Welcome, soldier, to Mission Rational Function. Today I'll brief you on all knowledge you will need to know to be able to survive in the harsh reality of Rational Island. In the enemy territory, expect to face challenges that include deciphering and simplifying, combining messages, solving different codes, drawing maps, and drawing information from mission brief. Factoring. When you first receive the message, check to see if there are any greatest common factors that can be pulled out of the equation to decode it. Then in this procession, check if it could be the difference of two perfect squares, a perfect square trinomial, or a quadratic trinomial. The discriminant can come in handy since it can be determined if a trinomial is factorable or not. Plug the values a, b, and c from ax squared plus bx plus c structure into b squared minus 4ac. If it is perfect square, then it can be factored. If it is not a perfect square, then it is prime and cannot be simplified and decoded. T-substitution is equating an expression to a variable, such as t. Though this doesn't change the math at all, it makes it easier to recognize patterns as one works through. Just remember to replace the variable with the expression at the end. Grouping works by grouping like terms together, using the associative property. These terms often have a common factor that cannot be factored out. Then you undo the distribution of the number in the parentheses and result have two factors. And now on to even and odd with higher powers than 3. First, factor the numbers in the expression so the power on the variable match the powers on the numbers. If the numbers are being added to the variable, the first parentheses will hold x plus the number. The second parentheses will start with x to the original power minus 1 multiplied by the number to the 0th power, equaling 1. Repeat this step, subtracting 1 power from the variable and adding 1 to the number until you reach 0 to the power of the variable and the original power minus 1 on this number. Alternate signs and numbers in between sets of multiplied numbers and variables. If the numbers are being subtracted, the first parentheses will hold x minus the number. So repeat the above steps with the subtraction in between each set of multiplied numbers. Adding and subtracting rational expressions. When you add and subtract any rational functions, you need to first go back to your basic training. In order to add and subtract any fraction, the denominator needs to be the same. This is the same thing for rational functions. If the sources have different denominators, we can't decode the message. When we add and subtract these expressions, we need to remember our handy decoder sheet. This has tips and tricks for success. First, we need to factor the denominator and cancel any matching factors. Then we define the least common multiple. After this, we can get a little clever by multiplying by a 1 in disguise. Don't get tricked by this 1, no matter how clever it might be. Now we need to combine numerators and cancel the matching factors. Be careful. Factors can only cancel if they are being multiplied. You can't cancel addition or subtraction by itself. Multiplying and dividing rational expressions. Although decoding rational functions that are being multiplied or dividing might seem tough, it can be easier than adding and subtracting. First, make sure to factor the numerator and denominator completely. After that, cancel any matching factors, but remember what these numbers are, because they will be the holes on your graphs. Then multiply like any other fraction, or reciprocate to divide. The great thing about multiplication and division is that the denominators don't have to be the same. Make sure you do not cancel any factors that aren't the exact same, or anything that are not being multiplied. Complex fractions. You may be faced with the complex fraction, which is any rational fraction with another fraction in either the numerator or denominator. To break this down into more understandable terms, you must multiply out the smaller fraction. To do this, either rewrite the numerator and denominator so they can consist of one fraction, or multiply out the smaller fraction using a smart form of 1. For example, x minus 5 over x minus 5. Either method will produce a normal rational fraction that can be decoded using multiplying and dividing techniques above. Solving rational equations. To solve the mystery of the code, you'll have to solve the rational equation. First, always see if the equation can be factored. After crossing any factors out from the numerators and denominators, set the denominators to 0 to find the domain busters. Note these domain busters. Then find the least common multiple of both denominators and multiply each term on both sides of the equation with the least common multiple. This should get rid of the fraction. Then you would use past algebra skills to solve for x. This is your answer, but root out any domain busters that were previously discovered as fake. If you come to any answer that is number equal to number, then there is an infinite number of solutions. When an answer such as 3 equal to 4, there are no solutions. Then it's mystery solved. Graphing rational functions. All messages that were sent can be turned into a map. These maps can guide you in the enemy territory if you follow them well. First, factor the denominator and find null x's by setting the factors to 0 and solving. This is where u, a spot, cannot pass or cross. Next, either draw a hole if the factors can cross that if it is also present in the numerator. This hole is a hole in the path of a function. To find the y-coordinate of the hole, plug the null x into the simplified version of the function and solve. If the factors do not cross out, draw a vertical asymptote in the form of a dotted line. It is not possible to cross this line. Then find the y-intercept by plugging 0 in the x and label in on the graph. After that, find the x-intercept by equating the numerator to 0 and solve. If the numerator is not able to equal 0, there is not x-intercept. Next, figure out how the functions will behave at the end. The function will either level off at a horizontal asymptote or not level off at all. The horizontal asymptote can be determined 3 ways. If it is top-heavy or the numerator has a higher degree, then there is no asymptote. If it is bottom-heavy with the denominator having the larger degree, the asymptote is at y equals 0. And then if both numerator and denominator have equal degrees, such as ax squared over bx squared, then the asymptote will be at a over b. After that, find how the function behaves around vertical asymptotes by plugging in numbers right next to the asymptotes. The function will either shoot off or swoosh off to positive or negative infinity. Finally, finish your map by connecting the rest of the graph so it's smooth and continuous. Use a calculator to label any obvious max or mins.